In late 2022, the Lambda functions processing background jobs for a B2B platform began timing out. No code had changed in 4 months. The functions had run successfully since deployment. 3 changes had accumulated quietly in the background. Average job payload size had grown from 150 kilobytes to 600 kilobytes, as customers added data fields over time. A dependency API had introduced rate limiting in a minor update, adding latency to every outbound call. And 2 new background job types had been deployed to the account, sharing the same concurrent execution limit and reducing the headroom available to the original functions. No single change would have caused a failure. Together, they had consumed every margin that had made the original configuration safe. The assumption at the foundation of most production configurations is that a system which passed its tests and ran successfully in production is a system that will continue to run successfully. This assumption has a shelf life. Nobody announces when it expires. Cloud applications do not operate in a fixed environment. The data they process grows. The services they depend on are updated by their providers. The infrastructure they share with other customers changes through platform releases. Features added to the account after the original deployment draw from limits that were previously available. None of these changes requires a code deployment. None modifies the application. All of them alter the relationship between the application's configuration and the ceilings it operates within. Limit drift is the name for this process. The configuration stays the same. The environment around it does not. The margin between current usage and the limit ceiling narrows, continuously, silently, without producing any alert, until the margin is gone and the limit that had years of headroom becomes the failure mode that surfaces at the next traffic event. Think about the water pipes in an older building. When the building was constructed, the pipes were clean. Water flowed at full pressure. Everything operated within its designed parameters. Over years of use, mineral deposits accumulate on the inner walls, a process called scaling. Each individual day's accumulation is invisible. Water still flows. Pressure is still adequate. The occupants notice nothing, but the effective diameter of each pipe is shrinking, and the maximum flow rate it can sustain is declining with it. Eventually, pressure on the top floor drops below the threshold where a shower and a washing machine can run at the same time. No single event caused this. The pipe did not fail. The water supply did not change. The accumulation of small, invisible deposits finally crossed a threshold, under demand conditions that had worked without issue for years. Limit drift operates on the same principle. The application runs. The limits are not hit. But the distance between current usage and the limit ceiling is narrowing through continuous, invisible accumulation. The configuration that had comfortable headroom when it was designed has almost none when the next traffic peak arrives. One difference from the analogy is worth naming. Pipe scaling is passive. Deposits accumulate regardless of what the occupants do. Limit drift can be influenced. Headroom can be monitored. Limits can be raised before demand reaches them. The accumulation can be managed, if not stopped. The analogy carries the invisibility and the gradualness accurately. It does not carry the possibility of intervention, and that possibility is the practical point of this video. Drift arrives through 4 channels. Most applications in production for more than a year are experiencing all 4 simultaneously. The first is organic growth. User counts increase, data volumes grow, request rates climb. Every increase consumes more of the same fixed ceilings, more API calls against the same rate limit, more connections drawn from the same pool, more storage approaching the same quota. Growth was the intention. Its effect on limit headroom was not modeled into the original configuration and rarely revisited as growth continued. The second is shared resource contention. Cloud accounts accumulate over time. Features are added, background jobs are introduced, new services are deployed into the same account. Many of these additions draw from limits that are shared across the account: concurrent execution pools, API gateway throttling ceilings, database connection limits. A new analytics job, consuming 50 concurrent Lambda executions, reduces the available headroom for customer-facing functions by 50, without any change to those functions, their configuration, or their own consumption pattern. The third is platform change. Cloud providers update their services continuously. Default behaviors shift. Performance characteristics of shared infrastructure are adjusted. A managed service your application depends on is updated in a minor release that changes its internal response timing. A dependency that previously responded in 50 milliseconds now consistently takes 90 milliseconds, not because of a fault, but because of an infrastructure update made by the provider. That change extends every Lambda execution duration by 40 milliseconds, moves the function closer to its timeout ceiling, and reduces the number of concurrent executions available at any given moment. The application code is unchanged. The consumption pattern has changed. The fourth is dependency evolution. Third-party APIs introduce rate limits in minor version updates. Internal services add new authentication steps. Response payloads grow as providers add fields. Each change propagates into the application's limit consumption in ways the application was not designed to account for, because the design predates the change and no review was triggered by a version bump in a dependency manifest. The accumulation pattern is what makes drift genuinely difficult to diagnose after a failure. Organic growth alone might not push the application past its failure threshold for 2 years. New features sharing the same limits might close that gap to 18 months. A platform change that slows response times might reduce it to 14. A dependency update might be the final contribution that empties the remaining headroom. When the incident occurs, no single cause is identifiable. The failure looks sudden. The monitoring history, reviewed afterward, shows the headroom had been declining for nearly a year. Drift cannot be eliminated. Growth is expected. Platform changes are outside the application team's control. Dependency evolution is continuous. New features will be added to the same account. The goal is not to prevent the accumulation, but to know when the margin has narrowed to the point where intervention is warranted. The monitoring practice that makes this possible is headroom tracking, measuring not the absolute usage of a limit, but the ratio of current usage to the ceiling. An application consuming 400 of its 1,000 available concurrent executions has 60% headroom. The same application 3 months later, consuming 870 of 1,000, has 13% headroom. The absolute number looks healthy in isolation. The ratio, tracked over time as a trend, shows an application approaching its ceiling and provides time to act before production discovers the arrival. Most monitoring setups track absolute usage by default, configuring alerts against headroom ratios, and, critically, tracking the rate of change in that ratio converts limit drift from a production surprise into a managed process. The configuration required to do this is available in every major cloud monitoring platform. It is not enabled by default. It requires a deliberate decision to treat headroom as a first-class operational metric, a decision most teams make once after their first drift-related incident. The B2B platform's Lambda failures were caused by 4 months of accumulation, no single change sufficient to produce failure, all of them together sufficient to eliminate the safety margins that had protected a correct, well-tested configuration. The limits had not changed, the environment had. A configuration is a snapshot of the fit between an application and its environment at a point in time. The application was designed for the data volumes, the dependency response times, and the account resource availability that existed at deployment. As each of those changed, the fit degraded. The snapshot became inaccurate. The margins that existed when it was taken did not exist when production next tested them. Drift is not an exceptional failure mode. It is the ordinary consequence of operating a live system in a shared, changing environment. Every production configuration is drifting. The only question is whether anyone is watching the headroom narrow and whether they act before the margin reaches zero.